So we will continue with duality theory, and this time I'll provide a more informal graphical illustration of all the things that we looked at in the last lecture. So this is the constraint optimization problem in vector form. We have to minimize this objective function f of x with respect to x, the primal variable, subject to the inequality constraints. G of x is less than equal to 0 and h of x is equal to 0. These are the inequality and equality constraints. The Lagrangian is Lx lambda mu, lambda and mu being the dual variables, which is equal to f of x, the objective function, plus lambda transpose times the g of x, the inequality constraint function, and plus mu transpose h of x, where h of x is the equality constraint, and this is the feasible set, the set of all points where the constraints are satisfied. And how do we construct the primal function? We simply maximize, take the supremum with respect to the dual variable. So we are eliminating the dual variables, lambda and mu, by taking the maximum. And then it becomes simply a function of x. So that's theta p of x. And so it's a mapping from n dimensions. X is n dimensional to one dimension. Okay, so this is the primal function. Next, the dual function is we do the opposite. So instead of taking the maximum with respect to the dual variables, we take the minimum, the infimum, with respect to the primal variable x, and thereby we eliminate x. We obtain a function of lambda and mu, and that's theta d of lambda mu. And always remember that lambda, according to our notation, our convention, where we are minimizing the objective function, and the inequality constraints are always of the form g of x less than equal to 0. And we have a plus sign here. In that case, lambda is always greater than equal to 0. For the equality constraints, the corresponding Lagrange multipliers, the mu's, can be positive or negative. Okay, so this is theta d of lambda mu. Once we extract the infimum with respect to x of the Lagrangian, we are left with a function of lambda and mu, and that's theta d lambda mu, the dual function. And that's a mapping from, since we have L number of inequality constraints, lambda is L dimensional, and since we have M number of equality constraints, mu is M dimensional, and so this theta d is a mapping from L plus M dimensional space to scalar quantity. And this is the definition which we have to remember. And keep practicing this, because it should, after you do a number of problems, this should be something right in your memory. You should be able to recall these instantaneously, instantly, once you are thinking about constraint optimization problems. Okay, and then we looked at a few properties. The dual function is concave. Okay, nothing about the primal yet. The dual function is concave. We've seen that. And we saw that the maximum of the dual is less than equal to the minimum of the primal. This is called weak duality. Theta d star is the maximum value of the dual function, and that is always less than equal to the minimum value of the primal function. And this is an outcome of the minimax theorem. If you take a function, you extract the maximum first and then the minimum, you'll get something that's always greater than equal to, if you do the opposite, if you take the minimum first and then take the maximum, you'll get something lower. And then if Slater's conditions are met, then strong duality holds. This is weak duality. Theta d star is always less than equal to theta p star, but under special circumstances, the Slater's conditions, theta p star becomes equal to theta d star. Okay, so now let's see how all of this looks graphically. So we restrict our attention to just a single inequality constraint at this point. No equality constraint. We have f of x equal to 0, f of x to minimize and subject to this scalar g of x less than equal to 0. Okay, and this plane here, this is g and this is f. This is the objective function, and we are trying to minimize. So we want to get values of f as low as possible. Okay, and we have the constraint g of x less than 0. Now, if we take any point x in n dimensions and find f of x and g of x, that gives a two-dimensional point in this FG plane. Okay, and so all these points, let's say we take all these, any point x here, all the way to plus infinity, minus infinity in any of these n dimension directions, and somehow they fall in this shaded region here. Okay, it could go towards infinity, but those are special cases. We just assume that f has lower and upper bounds, and g also has lower and upper bounds. Am I clear so far? So this is the FG plane. Given any x, we have this point in two-dimensional space, the FG plane, f of x, g of x.
Excuse me?
Yeah?
So f of x need not be convex in this case?
No.
Okay.
And since our constraint is g of x must be less than equal to 0, this is the g axis. And so g must be less than equal to 0. So this side is feasible, and the left side and the right side is infeasible. Okay, that's why I've shaded this part because gray, because it's infeasible. Okay. And so, given any x, now this is some x, which is in n dimensions, we can obtain fx and gx, this one. For some other value of x, and and so this is fx gx, and we can read off f of x by looking at the y-axis. So this is f of x, and likewise, this is g of x, right? This x is feasible because g of x is negative, it's -1. This is f of x, and this is g of x. This is, for some other value of x, the corresponding values of f of x and g of x. So this is another point in this FG plane. Will we get a point somewhere here or somewhere here? No. Okay, all the points will lie in this blue region. Now, what is theta p star? The minimum of theta p star. What happens in the infeasible region? What happens to theta p star? When
Infinity?
exactly, it's infinite, right? But in the feasible region, theta p star is
fx.
equal to f of x, right? So so we have to look at this region only. That's in the left half plane. Okay, where g is negative. And here, what's the minimum value of f? F, not g. Okay, as long we are restricted to this region, we don't care what the value of g is, as long as it's negative. Okay, so what's the minimum value of f you get here?
1.
No, it's this one here.
Oh, okay.
This. So we draw a tangent, that's a horizontal, the horizontal line is tangent at this point. So that's theta p star. Agreed?
Yes.
Yes.
So now we have located theta p star. Now we will try to find what is theta d star. Okay. So now that's going to be a little more complicated. So next we will locate theta d star. Okay. Are you guys ready?
Yes.
Good. So theta p star is located, and remember it has to lie in the feasible region. Right? So this is where we get a tangent and we can read off the value of this. That's theta p star. Okay, now let's look at the Lagrange multipliers. We only have a lambda, correct? And this is the Lagrange multiplier corresponding to this single inequality constraint. Remember that the Lagrange multiplier lambda has to be greater than 0, greater than or equal to 0. Okay, now you see these red lines here. These lines have slopes of negative lambda. And so they are of the form f plus lambda g equals constant. So everywhere in this line here, f plus lambda g equals some value. And for this particular case, lambda equals a -2, by the way. Sorry, lambda equals +2. Negative lambda is 2. The slopes of these straight lines are -2. And you can easily see that. You see, it crosses the x-axis at -1.5, the g-axis, and it crosses the f-axis at -3, right? So, and all these lines are parallel, so their slopes are obviously 2, -2. Okay, so everywhere in this straight line, f plus lambda g equals some value of the constant. Here it's equal to some other value of the constant. Here it's equal to some yet another value of the constant, and so on. Okay. In fact, for this straight line, what's this point here? F equals 0, g equals 3.5, correct?
Yeah.
So this is f plus lambda g equals 3.5. Here, this y-intercept, which is the f-intercept rather, is 2. The x-intercept or the g-intercept is 1. So this is f plus lambda g equals 1. Do you see that? This straight line is f plus lambda g equals -1.5. This one is f plus lambda g equals -4. This is point -4. Okay, so these are the contours of f plus lambda g equals constant for lambda equals 2. Are you guys with me?
Yes.
Yes.
Now, these are contours of f plus lambda g equal constant for another value of lambda. This was for lambda equals 2. This is for lambda equals 1. Okay, the slopes are -1. 45 degrees like this, right? Okay. And these are contours of f plus lambda g for lambda equals 0.5. Okay.
Yes.
So what do you see from here? Now, this was a higher value, right? Lambda equals 2. This is lambda equals 1. So notice the direction in which it's turning, okay? And this is for lambda equals 0.5. What will happen for lambda equals 0? It'll be purely horizontal, right?
Yeah.
Yeah.
Okay, so keep that in mind. So now, we want to, so this is what we have. Now, this is an x, and we have a point here. Okay, now, this is, let's say, we are given x, and lambda we are given 0.5. Okay, so we are given x, some value of x, we can find the point. And then we are given a value of lambda, and then we draw a straight line with slope negative lambda passing through this point. Okay, so the slope of this is for lambda equals 0.5 in this example. So negative half is the slope of this line, and it must pass through this point. Okay, so this is f plus lambda g equals constant, right? Now you can read off the value here. What's g? At this point, g is 0 and f is 1, right? At this point. So where this straight line intersects the f-axis, that gives you the value of the constant. Do you agree? The constant is 1 in our case.
Yeah.
Yes.
Now, we cannot have lambda equals negative 0.5. So positive slope, this is a line with positive slope. That is invalid. Why? Because lambda must be less than 0. Okay, lambda equals negative 0.5 for this one. The slope of this is plus 0.5. So that's not acceptable. Okay. Now, what happens? Now, I'll keep the dual lambda fixed at 0.5. Okay, and let's say I have a button. I tweak that button to change the value of x, or a joystick or whatever. I have something to adjust the value of x. Okay, as I change the value of x, I move in this blue shaded region, correct? And each time, so now from here, as I'm moving in this direction, what happens to the value of the constant? From here to here, what happened to the value of the constant? At this point,
Decreased,
the value of the constant is this, right?
decreased.
It's decreasing, it's decreasing, decreasing further, right? But for this point, when for some value of x, I arrive at this point, and then this is the value of the constant, right? And then I come here, this is the value of the constant. And then I come here. This is the lowest point, right? The value of the constant is this. Then if I come here, the value of the constant starts increasing, right? It was decreasing all the way here, and then it starts increasing. Do you see that?
Yeah.
Yes.
Yes.
Okay, so, and this was for lambda equals 0.5. And so with lambda equals 0.5, what am I doing here? In fact, I'm adjusting the primal variable x, right? Keeping lambda fixed, I'm adjusting the primal variable x. So what am I doing? What does this minimum value that I got here mean? Okay, so the minimum value is this, and that is theta d for lambda equals 0.5. Because theta d is when I minimize f plus lambda g with respect to x. Are you guys with me? This might take a little time to sink in.
Yes.
Yes.
Anyone with any questions, or do you need a little more time to think?
Yes, Dr. Das, I have a question.
Sure.
Yeah, when you are calculating the constant value, so we are always taking g as 0?
No.
Uh,
F plus lambda g equals constant. G can be anything, right?
yes.
But how do you find the value of the constant? By looking at the y-intercept.
Okay.
You're not setting g equals 0. Did we set g equals 0 here? No.
No. Yes, yes.
G has some value, this, right? But f plus lambda g, the value of that can be read off by looking at the y-intercept, which is the f-intercept in our case.
Yes, yes. Yeah.
Okay.
Dr. Das,
Can I ask?
Go ahead. Yeah, go ahead.
Yeah, I wanted to ask a question. How do we ensure that when we're choosing those points x, how do we ensure that we land on the minimum?
Not yet. Accidentally, I hit the minimum, let's say.
Okay.
Okay. It's just graphical illustration, okay? Just assume that somehow I hit the minimum. I'm not telling you how.
Mm-hmm.
So this is the point gx fx for some value of x.
Excuse me, Dr. Das.
Yeah.
So for different values of lambda, you will have different values of f plus lambda g. So our objective is to find an optimal value of lambda, or what? I mean, what value of lambda should we freeze at the end?
Our objective is right now to find theta d star, the maximum possible value of theta d. So
Okay.
for lambda equals 0.5, we found that this is the minimum,
Okay.
right? For
Okay.
some other value of lambda, we'll get some other minimum,
Okay. Okay.
right?
Yeah.
So let's look at that. So this is for lambda equals 0.5, we got this. For lambda equals, this is 2. Okay, so this is the minimum. What did we do here? In fact, we took the tangent with slope negative 0.5. This straight line is tangent to this blue region, right? And at the point of tangency, we get f of x and g of x, or rather g of x and f of x. And we can read off the value of f plus lambda g here. Agreed?
Yes.
So this is a tangent.
So Dr. Das, our goal here is to find the optimum value of x that minimize the f plus lambda g.
Yes.
Okay.
It's not optimal. We're just trying to find the minimum. Don't use the word optimal yet. If you look back at the definition, theta d lambda mu. All I'm doing is taking the infimum here, the minimum. I'm not saying anything about the optimum here. Okay, we'll get to that later. Just the infimum.
Yeah.
Okay, so this, we adjust x, somehow we have to find the infimum, right? And we got it right here. For this value of lambda, it's a function, theta d is a function of lambda, right? And so for lambda equals 0.5, theta d of 0.5 is this point. And how do we get that? By moving around, by taking the tangent with slope negative lambda. Now, for some other lambda, here for lambda equals 2, this is the point of tangency. And so this is theta d of 2, this guy here. Agreed?
Yes.
Yes.
And for theta d equals 1, this is the point, theta d. So theta d when lambda equals 1 is this point, because the slope of this straight line is -1. Okay, so for different values of lambda, I can now plot theta d of lambda. Agreed?
Yeah.
Yes.
Okay. Now, so how do I find theta d star?
By getting the minimum from the graph. Like if I graph the lambda with the theta d at each step, I get the minimum
So,
value.
so for different, I have to now change lambda, right? So I have to
Yes.
maximize with respect to lambda, right? I took the
Yes.
minimum with respect to mu. Now I have to maximize with respect to lambda, right? So for different values of lambda, I have to draw the tangent at each time I'm drawing the tangent, right?
Yes.
So these are for 3 different values of lambda. This is what I got. For lambda equals 2, this was theta d of lambda. For lambda equals 1, this is theta d of lambda. For lambda equals 0.5, this is theta d of lambda. It's moving up, right? And then for lambda equals 0.35, this straight line is a slope, is tangent. Or this straight line with slope negative 0.35 is tangent at both these points. Okay. And this is theta d star for lambda equals 0.35. What would happen if I reduced lambda further? Maybe lambda equals 0.25. What would happen then?
It's going to cross the invisible region.
How? So this, what will happen is then the straight line, okay, for lambda equals 0.25 would not be tangential here. It'll be tangential somewhere here, right?
Yes.
Yeah, this is for 0.15. Where is it tangent? Here in the infeasible region. So what's the problem? At this point, what's the corresponding value of x? It's in the infeasible region because g of x is 0.4.
Positive.
It's positive, right?
Yes.
So at this point where the straight line is tangent to both, that gives me theta d star. And can you see why theta d is a concave function? Because see, as I was decreasing lambda, it was, what was happening? It was going up when I was decreasing lambda. And then decreasing it further, after this point, it will start going down. Right?
Yeah.
So that's why theta d of lambda is concave. Okay.
Yes.
So this is my theta d star. And I have previously seen, okay, this is for lambda equals 0.15. And for lambda equals 0, it again goes down further, right? Theta d for lambda equals 0. So this is my theta d star. And this is my theta p star. And graphically, you can clearly see the duality gap here. Theta p star is more than theta d star. This is the duality gap. Okay.
Yes.
Here, for this case, what's the duality gap? 0. Horizontal line is tangent here. Here, the horizontal line would have been tangent somewhere here, right? In the infeasible region. Here, the horizontal line is tangent in the feasible region. Theta p star equals theta d star. For this situation, strong duality holds. What's that? Dania, were you?
Sorry.
Oh, I thought you had a question. Maybe I
No, no,
Okay.
no, no.
Okay. Now, convex function, convex constraint. So here, strong duality holds in this case. Again, strong duality holds. Because I can draw a tangent at this point. Okay. But for theta p star, I have to draw a horizontal right. I have to only consider the left portion in the feasible region and then find the minimum horizontal line. It's always a horizontal line. If I were to draw a tangent, it will be tangent to this point here. Theta p star equals theta d star here. Here, Slater's condition is not satisfied for this because there is no strictly feasible region. There is nothing, the entire blue shaded region, nothing crosses over to the left-hand side. So Slater's condition is not satisfied. You must have an X naught. If you remember Slater's condition, there exists an X naught such that G of X naught is strictly less than 0. So the inequality constraint is strictly satisfied. There must be at least one point that strictly satisfies the inequality constraint. But in this case, here, there is no such point which strictly satisfies the inequality constraint. Okay, it doesn't cross over to this side. So this is Slater's conditions for strong duality, and when strong duality holds, this is the saddle point. F of x is convex, gi of x is convex, hi of x is affine, hj, small typo here, and a strictly feasible solution exists, x naught. Now, let's do some examples in the tutorial at 6:30. Okay?
Sure.
Okay.
So see you guys then.
Okay. Thank you, Doctor.
Thank you.
Bye.
Thank you.
Thank you.